Hi, everyone. I hope everyone is doing well and had a wonderful Thanksgiving break. I'm here with Millie. We're here trying to get stuff done. Please make sure that you guys are on your very best behavior. We got less than 3 weeks. You guys can hang on, and you guys got this. Um, I'm going to be sharing my screen so that way you guys can see. I'm going to be going over our. I'm going to be going over our. Hold on. Google Meet has changed a little bit. So we are going to share this. Share. I got this. All right. So looking at our presentation window, we are going to go straight to this slideshow presentation. I hope you guys can still see it. There it goes. All righty. So when we're looking at our slideshow here, I apologize. I'm a little out of practice, y'all. All right, so we have stars. We're going to describe the life cycle of a star and compare and classify stars using the Hertzsprung-Russell diagram. So we have to be careful with the Hertzsprung-Russell diagram because you have to read your X and Y axis because the axes don't go in the typical order that you would expect in math. So when we look at the picture of the sun taken by NASA's Solar Dynamics Observatory, a satellite in orbit around Earth, the color is due to a filter that brings out the details of moving gas on the sun's surface. So there's a unit that we didn't go over yet, and we'll go over it when we come back, and it comes down to wavelengths. So when you think about back in 6th grade, 5th grade, all of the different grades where you've looked at different sound wavelengths, you've looked at the Doppler effect where, ambulances get louder as they get closer. You've looked at different wavelengths where, you think about the visible light spectrum where red is a very long wavelength, which is why we see red so well. And we look at sorry, having problems with Millie's little cart here. And we look at all the different colors and the different wavelengths. And as we take pictures in space, what we're doing is we're comparing what we know on Earth to what we know and what we see in space with all of these pictures, diagrams, all of these new telescopes and everything else. Because of all the telescopes and all of this is why we're able to see certain different things and why we assume that certain stars burn at certain temperatures because we compare it to what we already know because we lack the technology to get there, as we've discussed a few times with crazy Mr. Davis down the hallway. So until we can get that technology up to beat, which you guys should be able to see within your lifetime, we're still making a lot of conjectures. So just like we can't travel back in history, we can only study what is left by and study as an archaeologist from the evidence left. We can only study the evidence that we have access to. So looking at this picture of our solar flare on Earth, we use this filter so that way we can see those explosions and we can see the colors because we are looking at something so far away. Okay, remember to get to Mars, which is the next closest planet, we are looking about taking 20 years to get there. Okay. So like Miss Hamilton, by the time I'd get there, I should have been retired by then. Millie is going to have been looking at finishing college by the time we would get to Mars. So and we're talking about looking at the sun. So you have Mercury and Venus also there. So the sun is a literal star, is the literal star in our solar system. As we watch the sky, we see and follow in predictable patterns from day to day. It rises and sets each day, sunrises, sunsets, and tends to appear more colorful than the light from the midday sun. Yet while the sun may appear, different colors throughout the day. Now, make sure that you guys are really realizing that with stars, we typically see a star in the center of a solar system. And this is what we are noticing, especially with the Andromeda galaxy, which is the closest one that we have to us. So when you're looking at it, we look at studying the sun because it is our star. It is our source, our life source. We are the perfect amount of distance away from the sun to have life exist on planet Earth. And these solar flares, if you guys noticed in the month of October, and we see it again in about March or April, the radio stations tend to have issues. We used to see these issues. Oh, excuse you. We used to see these issues a whole lot more, especially when we have antenna TV, where we would lose stations, or like one of my first apartments, I had antenna TV because I couldn't get internet because of the tree cover around my house, my apartment. So I had to switch where my antenna was, and I almost had to redo my entire living room because the solar flares and the way that the sun reacts with our system is far enough away, but just close enough to kind of mess with some things. That's why you kind of tend to see that your cell phones are having issues, because they change with your wavelengths. They change the way your cell phone picks up all your different wavelengths. So when we look at this medium-sized solar flare here, we can combine or rephrase different questions, which is what they were asking you to do. So when we study other stars, what we're doing is we take what we know from the sun, because we can get this picture because we're close enough to get this detailed picture, and we apply it to further out in space. So when we look at our vocabulary, we have apparent magnitude, which is a kind of simple. I don't know what she's doing, y'all. She's bobbing with my talking, I guess. Um, so apparent magnitude is exactly what it says. Is, you're talking about, like when we were talking about Vector from Despicable Me, and you're talking about, magnitude and direction. Well, magnitude is how much. So apparent is just what are we noticing and what are we seeing with that. And then we have our HR diagram, which is the Hertzsprung-Russell diagram. We have the luminosity, which is how bright or how dim things are, and parallax. So parallax is something really simple, and there's a lab we typically do, but you can do it really quick with your fingers. So everybody take a pause, and as soon as I'm done, you guys have to stop and go back. So stick your finger out in front of your face, and this is how we kind of figure out if you're right eye or left eye dominant. And you close one eye, and then you close the other eye and switch back and forth. And when you see this move at this distance, now move it about halfway between. You should have seen a bigger difference. Okay, everybody stop. Stop. I know a couple of you are still trying. You should have seen a difference between far away and closer. So we use this parallax to measure things in space. So if we see them from just a slightly different angle, if they move a great distance, then we know that they are closer. If they do barely move, then we know that they are far away. And that's how we use parallax. So determining the star's luminosity. When a sun is out, you can't really see any other stars because it's blocking them out, because our sun is the closest star to us. The sky is just way too bright. At night, we can see many stars, and some of those stars seem brighter or dimmer than others, but the sky is still dark. So we can take this in one of two ways. You can take this as the bright stars are closer to us, but in more actuality, it's not only that they're closer to us, it also has to deal with how bright they are. So when we see these brighter stars, these bigger stars close to us, we use that vocab word apparent magnitude to show that these stars must be a little bit bigger or closer. So locations of stars in space. So constellations are groups of stars, and we do this, and this all came from mythology, starting back with those ancient Romans and ancient Greeks. We were talking about them with, we were talking about Newton's law. Excuse me. So we have our constellations, and they all typically have a Roman or a Greek name. But we do this so that way we can try to just make more common sense of it. But what you have to realize is that when we're looking at a constellation like Orion, we see it standing here on Earth, looking at it, and we see Orion this way. We see the belt, we see the shoulders, we see the legs. But if we were to be on Mars, we may not see Orion this way. We would see it in a different way. And so you cannot be solely reliant on constellations. This is where it becomes difficult to travel in space. So when you're on Earth, For instance, we'll take the movie Moana. Maui's always telling her, okay, you got to kind of measure, your horizon and your stars. And we can use stars, and stars have been used by sailors for centuries because they are constant. We have mapped them. We know the Aztecs, the Mayans, all of the ancient civilizations mapped the stars. So we know. But if we were to go into space and start traveling, we're even seeing this on the Mir space station, and that's really close to us in relative distance, that the constellations look a little different. So we have to find new ways to kind of classify or recognize these stars. So with parallax, this is that lab again. So again, remember parallax. Everybody do it with me. So the farther away, the less change. The closer it is, the more change it is. So less change, more change. Less change, more change. Everybody put your hands down. Okay. I got to go back to my meat tab. Hold on. All right. So when we go back to our presentation, because I'm the only one here, that we're just making sure. So when you view an object in space at distances from different locations, it can appear more relative to the background. This phenomenon is known as parallax. And you do need to know this vocab word, you guys. We have to learn parallax. We have to learn the HR diagram. These are big on STAR, which is why you're here with me. So what pattern do we notice with how the distance is? Well, we know the distance. The further away it is, the less change in view, compared to the closer it is, the more change in view. So scientists use parallax to determine this distance from Earth to the sun and other stars. When the distance to the first star, other than the sun, was measured using parallax, it was determined that the star was hundreds of thousands times farther from Earth than the sun. So when we're looking at that first star, we're seeing that because parallax tells us that the closer it is, the more difference we're going to see, which is why we see such a big difference in the sun. But that far away star, there wasn't really much difference depending on wherever we're looking from. So to the nearest star, or the nearest star to Earth aside from the sun, is Proxima Centauri. Proxima Centauri is about 268,770 times farther from Earth than the sun. We're not talking about miles or light years. We're talking about the distance. So, 2 times the distance, 10 times the distance. We're talking about over 270,000 times that distance, almost that. All right. So this will affect the apparent brightness of the sun. Because we're closer, it's going to be brighter. Okay, when we go to compare and classifying stars, we can compare the star's luminosity. So remember and recall that apparent brightness of a star depends on the distance and its luminosity. So how bright it is. Okay, and this is where it gets a little bit confusing. So your apparent brightness is what you can see with your naked eye or a basic telescope. But as we go into the HR diagram, which we'll go into a little bit further on Friday, you're going to see that the luminosity is just a little bit different. It has to do with how the star burns. So just think about how you have your the way a fire burns. So on the outside edges, you have the red. Like if you were to actually go into art and draw and paint a fire, you would have your red on the outside, orange down to yellow, down to more your white, your blue, and then your white hot. Same thing with the stars. So when they're talking about luminosity, they're talking about the temperature at which they burn. But when you're talking about apparent brightness, it's what you can see. So luminosity is commonly used to compare stars. In the same way that you can plot numbers on a number line, you can plot the luminosity of stars as well. This is a useful model for comparing stars. So on the STAR test and all of the practice questions we've seen modeled for the HR diagram, you have to be able to not only be able to read it, but you have to be able to explain it. And it's a very simple explanation. You guys just got to stick with me, all righty? So when we're looking at star color, astronomers classify stars based on a color or spectrum. These types are given letters to designate their spectral type. For example, the sun is a type G star. So our key shows the classification of those star colors. and we look at temperature in Kelvin. So when we can't measure by Celsius, which is what we use in science, we use Kelvin. So if you look, we're here, and it's fairly low in temperature, you guys. When we start looking at our red stars, we got less than 3,700 Kelvin. When we're looking at that white hot, like I was telling you, that really, really bright white, you have the blue and you have that fake white, and then you start going into your yellows and reds. So star color is just related to temperature, just like what we see burning here on Earth. Now, remember, we are taking what we know and we can prove here on planet Earth and applying it to what we're seeing in pictures that we're getting from telescopes. And we can't just say, I love to get with the Davis problem, but we can't just say that, NASA's fake, because private enterprises and private people are posting pictures that they are taking in space, and they're able to prove it as well. So just how, materials glow red hot when it is warmed, and it goes like this. This is how we compare it to stars. Okay, so it's just related to temperature. So although stars are composed of hot glowing gases, they follow the same pattern as steel. And we know this because we're able to prove it within an enclosed chamber in a physics lab. So like the colors of the hot steel, each spectral type corresponds to a specific temperature range. Star temperatures are measured in Kelvin, and you can plot star temperatures on a line to compare stars. This is a useful model for just comparing them. All right, you guys have access to this, so you guys are able to add these to your note sheet if you need to. So you have your different star temperatures, and you don't need to memorize. I know there's a couple of you that are going, oh my goodness, do I need to memorize all these letters? No, you don't. No, it's not worth it. Do not. I know there's a couple of you that every class period that are like, oh my goodness, she went too fast. No, you just got to read it. So as you're reading this, you know that our star is a G. That's what you guys need to remember. So I always say, go us. And that way you can remember that we have G is our star's type. All righty. And then we go into this Hertzsprung-Russell diagram. I'm going to briefly touch on it today before we finish. You guys need to work on your notes the rest of class. Do not mess around. This is your chance, and you guys are going to have a quiz, so you guys need to do this. The Hertzsprung-Russell diagram, or we like to call it the HR diagram, is something that just looks like this, you guys. You have this weird looking negative slope, and it's not really a negative slope. So don't think of it as your math. Do think about it that you have to read it like a table. So just like, we used to train you guys table label, do the same thing with your Hertzsprung-Russell diagram, and just double check, y'all. 2 letters to describe this diagram, because you have to double check your measurements. Because as you can tell, you can tell your cooler ones, you get redder all the way to that blue, and then you have the white here. Oh my goodness. I'm sorry. Millie's upset that she doesn't have all my attention. And so we have our luminosity. So we have the lower luminosity down at the bottom, and then we have the higher luminosity at the top. But if you guys were to look at the very bottom of it, your hotter stars are right here, and your cooler stars are out here. So when we're talking about planet Earth, we're talking about something that's more along out here, okay? When we're talking about those really old stars that are about ready to go black hole, or now we have our new white holes, when we're talking about all that stuff, we are talking about these really old stars down here. These are the ones that we watch. And so as the life cycle of the star, we have noticed this, especially with that Andromeda galaxy, which is really close to us, that we have been able to map a few stars. I'm talking barely, you guys. I'm talking like from this little point to this little point here. So small, because the life cycle of a star takes so long. So we're again applying what we know, and we're coming up with this diagram right here. Now you would be asked to read the diagram, like which one is the hottest and dimmest stars, and you're going to be able to go down here. We're going to label them as main sequence, supergiants, red dwarfs, and white dwarfs. So our main sequence stars, those are just the main stars we normally have. They vary in brightness, and most stars are these kinds of stars because they're in the main part of their life cycle. Just like you're an infant for just a little bit of time, you're a child for just a little bit of time, and we're kind of stuck in this adulthood until you get to, retirement age and getting to be old fart age. And then you start moving down to that wife door area. So we have our red giants, which are cooler but more luminous. Main sequence stars at the same temperature. So we have supergiants that are a range of different temperatures up here at the top, but they're very huge. They're very large. That's why they're way up there. We have our white dwarfs that are very dim and very hot. And then our red dwarfs are dim and cooler than most of the rest of the main sequence stars. So right before a red dwarf, like our red dwarfs and our white dwarfs are the ones that we watch for to be able to go into a black hole type situation. We're also watching our supergiants, our giants turning into these main sequence stars to look at the creation of new galaxies. Alrighty, so we're going to stop there, and I'm going to go back over the HR diagram again on for Friday's video. You guys are going to see me in the same clothes. I'm sorry, you guys are just stuck with me. Again, I hope you guys are doing well and have a great day today. Be awesome. Do great things, please.